Geometry, guys. Today we're going to talk about postulates, and then we're going to write some proofs using postulates and using deductive reasoning to do that. And we're going to talk a lot about the transitive property in the second half of this. But right now we're just going to use the postulates that are given to us. And a postulate is a statement that's just accepted as true. We just understand the way things are written and the way things relate to one another. So we accept that postulate as true. So I'm going to get rid of this statement, and I'm going to put up a bunch of postulates. Postulate 1, through any 2 points, there's exactly one line. And that sort of makes sense. You know, you could draw points. You could say, okay, well, this line, this point, and this point down here, there's only one line that goes through it. Where's my line? Where's my line? Here's my line. You know, there's only one line that cuts through both of these points, and it's that guy right there, right? I'll take those away. And you do understand that that makes sense. Any 3 non-collinear points, there's exactly one plane. That makes sense. If you have three points that are not in a line, right? They exist only on one plane. Like you see this flat green screen here, that's our plane, right? That's where they're sitting. A line contains at least 2 points. You can't have 1 point and a line, right? A line, even if it's, you know, this dot right here, there's a line that goes through it. It cuts through those 2 points, okay? A plane contains at least 3 non-collinear points. Through any 3 non-collinear points, there's exactly one plane. I kind of accept both of those as interchangeable. I like 2 because it's more concise. If 2 points lie in a plane, then the entire line containing those points lies in that same plane. If 2 lines intersect, then their intersection is only 1 point, right? You got a line here, a line here. There's only 1 point where they intersect. Good? Now, when planes connect, they intersect in a line. Their intersection is a line, right? So you got a plane here, and you have another plane that goes down through it. That's behind it, right? And comes through, right? And where they intersect, right through here-ish, it's just this one line. All right, that's a horrible drawing, and I apologize for it. I don't even think I'm going to be able to get through all of this by erasing it all. I lied. It worked. Okay, so let's start looking at problems and see if these guys work. Let's see. A line contains exactly 1 point. What? A line contains at least how many? 2 points. That is a statement that is always, sometimes, or never true. Never. Never true. A line can't contain only 1 point. Non-collinear points R, S, and T are contained in exactly one plane. Okay, well, look back up here. Postulate 2.2 says, through any 3 non-collinear points, there is exactly one plane. Well, that fits this definition exactly. So we're going to say this is always true. Any 2 lines, L and M, intersect. Well, they don't always intersect, right? Sometimes you have parallel lines. So they're not always going to intersect. Sometimes they'll never cross. So we'll just say sometimes. And these are just logical statements, right? Sometimes it's true, sometimes it's not. This is always true. That's never true. If points G and H are contained in plane M, then the line GH is perpendicular to plane M. Perpendicular? But if they're on the plane, let's say that we have a plane, right? We have a plane and we have 2 points on it. Do they stick out at a 90-degree angle? No, they run right along the plane. They're parallel with the plane. So that is never true. Never. If they're contained in the plane, they cannot be perpendicular. So planes R and S intersect in point T. Let's see. If 2 planes intersect, then their intersection is a line. Nope, a point is not a line, right? We can't have one point and make a line. So this is never true. Now, if points A, B, and C are collinear, then their segments, AB, BC, and CA, are contained in that exact one plane. And that happens to be true. If all 3 points lie on the plane, right? Here's our plane again. And we have A and B and C, right? AB is here. That's still on the plane. BC is here. It's still on the plane. And CA. All 3 are contained in that plane. Those line segments are contained in that plane. So that is always true. Always. Good. All right, we'll move on. Now, this is kind of semi-interesting. State the postulate that can be used to show each statement is true. Exactly one plane contains F, B, and E. F, B, and E. F, B, and E. They do not exist on the same line, right? They are 3 non-collinear points. Therefore, through any 3 non-collinear points, there is exactly one plane. Exactly one plane contains F, B, and E. There it is. All right, so we're going to say that's postulate 2.2 tells me so. Cool? All right, B and E lies in plane Q. B and E lies in plane 2. If 2 points lie in a plane, then the entire line containing those points lies in the plane. Look at that. 2.5, postulate 2.5 states exactly that. Right? Postulate 2.5. I don't know why I write 1, 2 this way and 1, 2 this way. That's goofy. Sorry about that. Here we go. We're moving on. Moving on. Hey, I can get rid of the postulates. Goodbye, postulates. Now we're going to talk about proofs. Paragraph proofs. These are probably the most difficult part of the writing in geometry. And so to do this, and I apologize, I'm going to show you the book answers when I do this, because I want you to learn a certain couple of sets of words, okay? Really and truly, I want you to remember the transitive property. Transitive property means it just transmits from one to the other, and then this to another. Therefore, this is the same as this, right? If A is equal to B and B is equal to C, then A is equal to C, okay? That's what the transitive property states. So now, I'm going to get rid of all those. Let's see what this says. I guess I can leave that up, right? Oh, look at that. I just did it. If A is congruent to D and D is congruent to E, write a proof that shows that A is congruent to E. Well, we just said the transitive property states that that's true, and we know the definition of congruence means that these are equal to each other, right? So A is congruent to D and D is congruent to E, then A is congruent to D and D is congruent to E. Wow. So we restate what we've been given, A to D, D to E, then A to D, and D to E. And finally, we restate through, when we call this the definition of congruence, right? All these things stated, right? So we restate them and we say that that's the definition of congruence. And then we say, okay, well, if we understand that the definition of congruence means that the measure of angle A is the same as the measure of angle E, we use the transitive property to get there, right? 1 is equal to 2, 2 is equal, and 2 is equal to 3, or 2 is congruent to 3. We're going to show that. So 1 is congruent to 2, and 2 is congruent to 3. Then 1 is the same magnitude as 2, and 2 is the same magnitude as 3 because of the definition of congruence. So angle A is the same as angle E by way of the transitive property and definition of congruence. So transitive give me a second. The transitive property and the definition of congruence. Good? Well, it's a long way around just to get to that silly answer. Let me move this up. We're getting close, guys. Okay, let me pull this out. If BC is congruent to EF, so these two line segments in total, they are congruent. That means they have the same length. So we can say that BC is equal to EF, right? We're going to talk about the definition of congruence. Then we're told that M is the midpoint of BC and N is the midpoint of EF. And we're going to write a paragraph that shows that BM, this line segment here, is the same as this line segment. And here we go. This is the fun, right? We're going to talk about the definition of congruence and the transitive property. Can we talk about the multiplication property of equality? Sure, we can multiply both of these by a half because of the definition of a midpoint. But not necessary. So we definitely can say BC is equal to EF, and that half of BC is equal to half of EF, because if you multiply both by a half, the multiplication property states that that's true. Thus, BM and EN use the transitive property. Okay? So restate. Tell me that they're equal due to the definition of congruence. And then you can tell me that their segments are equal by way of the transitive property. If I lose out on multiplying both by a half, the big segments by a half because of the midpoint idea, I'm not going to die. It would be nice, though, that you understand the property of equality. Last but certainly not least, this is the longest one of all, right? This is the one that states S is the midpoint of QP. So this is the midpoint here. P is the midpoint of ST. And T is the midpoint of PR. All right? That's what they all say. I did it in a different order, but that's what it says. Write a proof that shows that this line segment right here, QS, is the same as this line segment here. Well, here we go. We have a midpoint and a midpoint and a midpoint. And all these things end up being congruent. All these line segments, QS, SP, PT, TR, they're all congruent. Now, we're going to show S is the midpoint of QP. So QS is equal to SP. P is the midpoint of ST. So SP is equal to PT? Well, we just said that SP is equal to QS. I think we're going to take one more step. Thus, QS is equal to PT. That's what I just said by the transitive property. T is the midpoint of PR, so PT and TR are equal. Therefore, QS is equal to PR by way of the transitive property. Look at that. I just said the same thing. Only this used the mathematical language of the transitive property. Sorry, the transitive property. Okay, super simple. You guys got it. Work on that worksheet that I hand you, and you should be good to go. If you have any questions, please let me know. Not so sure I have enough time to get you that quiz I promised you on Wednesday or Thursday. We may have to push it off to next week. Thank you. Bye, guys.